But here is where honest science has to slow down, and this is exactly the part of the story that responsible reporting on this topic cannot skip. The research team has been explicit, repeatedly, that 4 observations alone are not enough to confirm this finding. Their own published statement includes a direct, careful qualification. The current date A cannot yet rule out the possibility that TRAPPIST-1e is simply a bare rock with no atmosphere at all. The evidence leans in an exciting direction. It does not yet cross the threshold scientists require before calling something a confirmed discovery. This matters enormously for understanding this story correctly, and it is worth explaining exactly why the uncertainty is still this large, even after all that careful analysis. Detecting an atmosphere this way is an extraordinarily delicate measurement. TRAPPIST-1e is a small, rocky planet, and the amount of starlight that actually grazes its atmosphere during a single transit is a tiny fraction of the star's total light. Layer the star's own contaminating activity on top of that already faint signal, and you end up with a measurement sitting right at the edge of what even Webb, the most powerful space telescope ever built, can currently detect with full confidence. So the research team did what careful scientists do when a first result is promising but inconclusive. They went back for more data. As of the most recent reporting on this project, an additional 15 transits of TRAPPIST-1e were already underway, expected to be completed by the end of 2025, bringing the total number of Webb observations of this single planet from 4 up to nearly 20. This next round of observations uses a smarter, more targeted strategy than the first attempt. Rather than observing TRAPPIST-1e alone, the team is pairing those observations with transits of TRAPPIST-1b, an inner planet in the same system that earlier Webb observations have already confirmed is almost certainly a bare rock with no meaningful atmosphere at all. Here is why that pairing matters, and it is a genuinely clever piece of scientific reasoning. Because TRAPPIST-1b and TRAPPIST-1e orbit the same star, both planets' transit data get contaminated by the exact same hot and cold active regions on the star's surface. But since TRAPPIST-1b has already been confirmed as a bare rock, any absorption signal appearing in its data has to be coming entirely from the star itself, not from a planetary atmosphere. Researchers can use TRAPPIST-1b's data almost like a calibration tool, precisely, mapping out what the star's own contamination looks like, and then subtracting that exact same pattern from TRAPPIST-1e's data. Whatever signal remains afterward, if it is a genuine, consistent signal rather than leftover noise, can be attributed with much greater confidence to TRAPPIST-1e's own atmosphere, rather than to the star sitting behind it. This approach represents a meaningful evolution in how scientists are tackling one of the hardest problems in modern exoplanet science, and it did not emerge without some healthy skepticism from within the scientific community itself. Astronomer Ignace Snellen, commenting on the research after congratulating the team on what he called fantastic work, raised an important, candid question about the technique's own limits. He wondered aloud whether transmission, spectroscopy, the general method being used here, might be approaching the edge of what it can reliably achieve for planets this small and stars this active, suggesting that the overwhelming noise generated by the star's own behavior could eventually become too large an obstacle for this specific technique to overcome on its own. That is a genuinely important, honest voice to include in this story because it reflects exactly how real scientific progress works. Nobody involved in this research is claiming certainty. The original team is pushing forward with a smarter, more rigorous method, specifically because their first attempt left real, acknowledged uncertainty behind. Outside scientists are raising legitimate questions about whether the underlying method itself has fundamental limits. Both of these things can be true at once, and both are part of the actual, complete scientific picture here, not just the more exciting and honestly marketing-friendly parts of the story. It's worth pausing here to explain exactly why scientists cannot simply add more observing time and expect a clean, unambiguous answer to emerge automatically. The problem is not solely about gathering enough total data. It is about correctly separating 2 overlapping signals that arrive mixed together every single time. A star like TRAPPIST-1 does not sit still and quiet while astronomers observe its planets. Its surface activity, the pattern of hotter and cooler regions, genuinely shifts and changes over time, meaning the specific contamination affecting one transit will not perfectly match the contamination affecting the next. Untangling a moving, evolving source of noise from a faint, consistent planetary signal underneath it is considerably harder than simply averaging together a larger pile of data and hoping the noise cancels out on its own. This is precisely why the team's decision to use TRAPPIST-1b, a planet already confirmed to have no atmosphere, as a kind of real-time calibration tool matters so much. It gives researchers an actual physical reference point for what pure stellar contamination looks like. gathered from the very same star, under very similar conditions, rather than relying purely on theoretical models of stellar behavior. So why has this particular set of results generated so much attention and excitement across the scientific community if it hasn't actually confirmed anything yet? Because of what TRAPPIST-1e represents in the much bigger picture of the search for life beyond Earth. For decades, the entire concept of detecting a potentially habitable atmosphere on a rocky planet orbiting another star existed almost entirely in the realm of theoretical planning and future mission proposals. Scientists spent years building instruments, developing techniques, and running simulations specifically preparing for the day a telescope powerful enough to attempt this measurement would finally exist. Webb is that telescope, and TRAPPIST-1e represents one of the very first genuine, serious attempts to put the decades-long preparation into practice on one of the best real candidates available. Nestor Espinosa, an astronomer who led one of the published research papers on this observation, captured that sense of a genuine turning point directly, describing the moment as measuring the details of starlight around Earth-sized planets 40 light-years away, and beginning to learn what it might actually be like there, if life could somehow be possible. He described the current period in astronomy plainly as a new age of exploration. 40 light-years from Earth, there is a small, most want to find something. And for the first time, the James Webb Space Telescope has actually looked closely enough to say it might not be empty after all. The planet is called TRAPPIST-1e. It orbits a tiny, cool red star tucked into the narrow band of space around that star where temperatures could allow liquid water to exist on a planet's surface, the region astronomers call the habitable zone. For years, TRAPPIST-1e has been near the very top of the list of places scientists most want to search for signs of a genuinely Earth-like world beyond our own solar system. In 2023, Webb finally turned its instruments toward it. It took scientists more than a year just to make sense of the data. And when they finally did, what they found was not proof of an atmosphere. It was something more careful, and in some ways more interesting. Real evidence that leans toward the planet having one, evidence that scientists cannot yet fully confirm and cannot yet fully rule out either. So here is the real question worth asking. What did James Webb actually find at TRAPPIST-1e, and why are scientists calling this one of the most important observations eye in the search for another habitable world, even though they still cannot say for certain what this planet actually looks like? To understand why this particular planet matters so much, you first need to understand the system it belongs to. TRAPPIST-1 is a small, dim, ultra-cool red-dwarf star, considerably smaller and cooler than our own sun. Discovered to host planets back in 2016 and more fully mapped out in 2017, the system turned out to be one of the most remarkable ever found. 7 rocky, roughly Earth-sized planets, all orbiting the same small star, packed into a space far smaller than the distance between our own Sun and Mercury. Because the star is so dim, several of these planets, despite orbiting extremely close to it, still sit in a temperature range where liquid water could theoretically exist. 3, sometimes described as 4 depending on where scientists draw the boundary, of the 7 planets fall within this habitable zone. Among all of them, TRAPPIST-1e stood out early on as the most promising. It sits almost perfectly in the middle of the habitable zone, receiving roughly the same amount of energy from its star that Earth receives from the Sun. Its size and mass are close enough to Earth's that many scientists consider it the single best rocky exoplanet candidate currently known for potentially supporting the right conditions for liquid water. That reputation is exactly why Webb pointed its most sensitive instrument directly at it, as part of a larger dedicated research campaign. It helps to understand just how strange and different this system looks compared to our own. TRAPPIST-1, the star itself, is so small and so cool that all 7 of its known planets orbit closer to it than Mercury orbits our Sun, and yet several of them still sit in a temperature range friendly to liquid water, purely because the star itself gives off so much less heat and light than our Sun does. If you stood on the surface of TRAPPIST-1e, the neighboring planets in the system would appear far larger and closer in the sky than any planet ever appears from Earth, some of them potentially large enough to show visible surface features to the naked eye, a detail that gives some sense of just how tightly packed and unusual this entire planetary system really is. That campaign has a name: DREAMS, short for Deep Reconnaissance of Exoplanet Atmospheres Using Multi-Instrument Spectroscopy. The project uses Webb's near-infrared spectrograph, an instrument that doesn't just take a picture of a planet, but breaks apart the tiny amount of starlight passing near or through a planet's atmosphere into its individual wavelengths, revealing the specific chemical fingerprints hidden inside that light. When a planet passes in front of its star, from Webb's point of view, a small fraction of the star's light grazes the edge of the planet, and if that planet has an atmosphere, certain wavelengths of that light get absorbed by the gases present. By carefully measuring which wavelengths are missing or dimmed, Scientists can figure out what a planet's atmosphere might actually be made of without ever needing to send a spacecraft anywhere near it. This method, called transmission spectroscopy, has already proven itself on larger planets, mostly gas giants, where the amount of starlight passing through a thick atmosphere is relatively large and easier to measure. Applying the same basic technique to a small, rocky, Earth-sized world is a considerably harder challenge, simply because the amount of light involved is so much smaller to begin with. TRAPPIST-1e represented one of the first serious tests of whether this method could actually work on a planet this size, orbiting a star this dim, at a distance this far from Earth. Between June and October of 2023, Webb observed TRAPPIST-1e passing in front of its star on 4 separate occasions, gathering exactly this kind of data each time. And almost immediately, the research team ran into a serious complication. The starlight itself was contaminated, not in the sense of anything going wrong with the telescope, but in a more fundamental way, tied to the star TRAPPIST-1 itself. Red-dwarf stars like this one are often covered in active regions, similar in principle to sunspots on our own sun. Some patches hotter than the star's average surface temperature, others cooler. As the planet passed in front of the star, the light Webb collected carried signatures from both the planet and these uneven, shifting hot and cold patches on the star's surface, tangled together in the same signal. Separating the planet's true atmospheric fingerprint from this stellar noise turned into a genuinely difficult technical problem. Dr. Ryan McDonald, an astronomer at the University of St. Andrews who worked on the research, described the challenge directly. He explained that when the 2023 observations first came down, the team quickly realized the star's contamination was making the search for an atmosphere extremely difficult. It ended up taking the research team more than a full year of careful, painstaking analysis just to reliably separate the star's own noisy signal from whatever the planet itself might be showing. This is the first real turning point in the story, because once that separation work was finally done, the results that emerged were genuinely intriguing. The data did not show a clean, obvious, unmistakable signature of an atmosphere. What it showed was something more nuanced. According to Dr. MacDonald, the most exciting possibility raised by the data IS that TRAPPIST-1e could have what scientists call a secondary atmosphere, one containing heavier molecules like nitrogen, similar in some ways to the type of atmosphere Earth itself has, rather than the light, primarily hydrogen, and helium atmospheres more typical of gas giant planets. Researchers also raised a second, equally interesting possibility, that the data could be consistent with something resembling the thick, hazy, methane-rich atmosphere found on Titan, Saturn's largest moon, one of the only other places in our own solar system known to have a substantial atmosphere and even stable liquid on its surface, in Titan's case, lakes of liquid methane rather than water. Both of these possibilities point toward the same broader conclusion. The data leans toward TRAPPIST-1e having some kind of real atmosphere, rather than being a bare, airless rock with nothing surrounding it at all. It is worth pausing on exactly why that framing is accurate rather than exaggerated. This is not a story about scientists claiming they have found life, or even claiming they have found a confirmed atmosphere. It is a story about scientists finally reaching the technical capability to ask the right question, in a way precise enough that the answer, whatever it eventually turns out to be, will genuinely matter. For most of the history of astronomy, humans could only guess at what the atmospheres of planets around other stars might look like. Right now, for the first time, researchers are gathering real, if still incomplete, physical evidence directly from one of the best candidates in the search for another habitable world. There's also a bigger, longer-term context worth understanding, because TRAPPIST-1e is not the only piece of this puzzle, and Webb is not the only tool being built to solve it. NASA's Pandora mission, a smaller dedicated satellite designed specifically to monitor stars hosting potentially habitable planets during transits, is expected to add complementary data to exactly this kind of research. Further, down the line, NASA's planned Habitable Worlds Observatory, a large next-generation space telescope specifically designed to search for biosignatures, chemical signs of life, on planets around other stars, represents the next major leap after Webb in this entire line of research. TRAPPIST-1e is not the final word in this story. It is one of the opening chapters in a research program scientists expect to run for decades. It is also worth remembering just how young this entire field of study actually is. The technology capable of even attempting a measurement like this did not exist a decade ago. Webb itself only began science operations in 2022. The specific technique being refined here, using one planet's confirmed bare rock data to calibrate the search for an atmosphere on a neighboring planet, is itself a genuinely new approach, developed specifically in response to the challenges this system presented. Every year that passes brings improved analysis methods, additional observing time. and eventually entirely new instruments built to pick up exactly where Webb's own limits are eventually reached. The uncertainty surrounding TRAPPIST-1e today is not a sign that this question is unanswerable. It is a sign that we are still in the earliest working stages of a genuinely difficult measurement, one that improves a little more with every additional transit scientists manage to observe. So, coming back to the central question this video started with, did James Webb really find that TRAPPIST-1e is not empty? The honest, careful answer is this. Webb found evidence that leans in that direction, evidence detailed enough and specific enough that leading researchers in the field consider a secondary, nitrogen or methane-rich atmosphere a genuinely exciting possibility worth taking seriously. What Webb has not done, and what the scientists behind this research are explicit about, is confirm that finding beyond reasonable doubt. The bare rock scenario remains firmly on the table and will stay there until the additional data currently being gathered either strengthens the atmospheric signal or reveals it was mostly noise from the star all along. That distinction is not a disappointing footnote to an otherwise exciting story. It is the actual substance of how real scientific discovery happens, especially for a question this consequential. A planet 40 light-years away, sitting in almost exactly the right place around its star, showing genuine hints of an atmosphere that current instruments cannot yet fully confirm, is a far more honest and, in its own way, far more compelling story than a premature declaration of certainty would ever be. Somewhere out there right now, TRAPPIST-1e continues its tight, quick orbit around its small, dim red star, passing in front of it again and again, each transit adding a little more light for Webb to study, a little more data for scientists to sift through. Within the next year or two, researchers expect to finally know, with real confidence, whether this planet is wrapped in an atmosphere capable of supporting liquid water, or whether it is simply another bare, silent rock circling a star 40 light-years from home. Either answer will matter. And for the first time in the history of astronomy, humans finally have a real working chance to find out.